Yeah, so thank you to Drew and Rachel for the invitation. And I also wanted to thank Hiram for the announcement about the Strike for Black Lives. And for those people who follow the IDEO seminar, the online arithmetic dynamics seminar, that is also shut down tomorrow in sort of collaboration with us, or so that we can participate as well. So I encourage you all to take that time to participate in the Strike for Black Lives, and that the IDEO seminar is moved to Thursday this week. So I guess I want to tell a bit of a story here about some work in related to a particular question in arithmetic dynamics that I've been working on, that some other people have been working on. And I realized putting together these slides that it's been now sort of 10 years that we've been thinking about this. I guess this talk is sort of aimed at people who don't have so much of an arithmetic dynamics background. So I'm hoping to sort of expose some people to some of the early motivation of this, and then extend into what I'm currently working on, what some other people are currently working on, and maybe some interesting questions moving forward about the critical height of an endomorphism of projective space. So I want to start by just sort of talking about the basic problem. Okay, the basic problem of dynamics is you have some sort of function. I mean, let's be very vague right now. You have some sort of function from a set to itself, and you have some sort of initial value z, and then you sort of repeatedly apply this function and generate a sequence by repeated application of the function. And the question is, what happens? What can you say? Right? And of course, it depends on what the context is, depends on what the structure of the set or the function is. And in the sort of early burst of activity in dynamics about 100 years ago, the focus was, sort of complex analytic structure, complex behavior. Everything was over the complex numbers. So here, just to give you some idea of like a classical result in dynamics that sort of motivates a little bit of this talk. This is a classical result. I guess maybe it's sort of more accurately attributable to Julia, but everything's a little blurry from this time. So let f be a polynomial of degree at least 2. Then the Julia set of f is connected if and only if all of the orbits of the critical points are bounded in the complex plane, so bounded away from infinity. And so just to sort of make sure that we're all on the same page here, that a critical point is a point of ramification, is a point where the derivative vanishes, right? So for a complex polynomial, this is just the first year calculus definition of a critical point. Okay, so what is the Julia set of a polynomial? Well, for the purposes of this talk, it's not too important, actually, that you understand what this is. You've all seen, the calendars with pictures of Julia sets. If you were at Holly's talk not last week, but last time at VaNTAGe, you will have seen some images of these Julia sets. It's sort of the domain of chaotic behavior of F with respect to iteration. But once you define this set, there are a bunch of natural questions you could start asking. Can it ever be empty? Can it ever be the whole plane or Riemann sphere? And quickly you get to the question of, is it connected? Is it disconnected? Sort of these basic topological properties. And the point of this statement is just that the connectedness, this sort of basic topological property of the dynamics of F as a whole, is determined, or maybe more accurately detected, by the orbits of the critical points. So the orbits of the critical points tell you something about the dynamics in general. And that'll be a bit of a theme, I guess, of this talk. But it's also just sort of a motivation. Well, in part, it's a motivation for this next definition. So if I have a particular polynomial or rational function in mind, and I want to convince you that it has bounded critical orbits, well, if it should happen that all of the critical orbits are actually finite, then my task in convincing you is much easier, right? I mean, I don't have to come up with any sort of complicated argument. If I start at a critical point and I start iterating the function and I eventually get into a periodic cycle, then you're convinced that that's going to be bounded. So this talk is not exclusively about post-critically finite rational functions, as have been some other talks that I've given, but they will feature heavily. And this is, for now, just sort of an example of a type of rational function where you could really quickly convince me that all the critical orbits are bounded. So question 1 about these things, of course, is, do they exist, right? So if I stipulate that a rational function has all its critical points pre-periodic under iteration, does that leave out all rational functions? And so I wanted to give some examples here. Here's a really simple example of z cubed. And of course, you could take z to any positive integer power, I guess not 1. All of my rational functions, unless I say otherwise, will have degree at least 2. Z cubed has two critical points, 0 and infinity. And if you cube 0, you get 0. And if you cube infinity, you get infinity. So there you go. That's post-critically finite. So that's kind of a silly example, but it at least convinces you that I'm not sort of making a vacuous definition here. Here's a slightly less trivial example, but again, you can check this. So in all of these examples that I'll show you, I have the critical points listed along the top. The size of the bubble is just whatever LaTeX decides the size of the bubble needs to be to encapsulate the symbol. That's one of the most common questions that I've gotten when I've shown these slides is what does the size of the bubble mean? And actually, so, I mean, I'll come to this later. It occurred to me as I was thinking about this particular talk that my standard answer of it means nothing is not really true. It kind of means the height of the number to some extent, but I'll come back to that later. But anyway, here is, again, some simple example that you can check by taking derivatives and plugging things in. Another simple example, a very similar looking polynomial, but just slightly different behavior. And one thing I should mention is that the fact that these values are different isn't particularly interesting. So when we're talking about dynamics, we usually think about up to change of variables. So of course I could change the variables and make these three values pretty much anything I wanted by doing the automorphism of P1. But the actual directed graph here is different, and that's an invariant, coordinate-free invariant. So those two examples are fundamentally different. And I just have a bunch of examples here just to show you. All of these examples happen to be cubic polynomials, and they happen to all have rational coefficients. And in part, this is just because I tried to write down every example I could think of with rational coefficients, every example of a cubic polynomial, which is post-critically finite. And the point is just to convince you that there are some of these things. So here's an example. So now these bubbles start to get really big, right? Because just LaTeX is having trouble fitting these things in here. So there's sort of a natural reason from the point of view of complex dynamics to be interested in these things. And it's maybe not surprising given the role that the critical points play in ramification if you're going to do some sort of study of the covering spaces that iteration of F generates. But I wanted, because this is a primarily number theory audience, number theoretic audience, I wanted to bring in a sort of motivation from algebraic number theory. So I am not going to talk about arboreal Galois representations. But other than to say this, so there's a sort of natural number theoretic question you can ask once you have a rational function and some point, again, degree at least 2, and some point on the projective line, well, you can sort of build this very natural tower where you sort of take pre-images. And for the purposes of this example, let's just say I'm taking all pre-images just to be specific. So I can generate, let's say K is a number field, or whatever kind of field, but for specificity, let's make it a number field. And I can take K and adjoin the pre-images of alpha by F, and I can adjoin the pre-images of the pre-images and the pre-images of the pre-images and so on, and I get this tower of fields. And I'll just denote the limit of this by K infinity F sub alpha. And this is a very natural sort of construction. This has a sort of Iwasawa theoretic flavor. Maybe if alpha is 1 and F of Z is Z to the P, maybe that is like exactly the construction there. But anyway, this is a sort of general construction you can do, and you can ask all sorts of questions in the number theory context of what can you say about this tower of fields, right? So we have probably an infinite algebraic extension. What sorts of interesting things can we say about that? And here's a theorem that speaks to that. That's again, just sort of trying to build buy-in for interest in these post-critically finite rational functions. So maybe I'll do the short part first, which is the statement of the theorem, and then I'll go to the attribution line. So let f of z be a rational function of degree at least 2, and let alpha be a non-exceptional point, and I'll say what that means in a second. But then this field K infinity F comma alpha is finitely ramified if and only if F is PCF, post-critically finite. So finitely ramified here means ramified above finitely many primes in the number field. So what does non-exceptional mean? Well, it means that the iterated backward orbit of alpha actually is infinite, right? So it basically means that this extension is actually an infinite algebraic extension, but you can be much more specific than that. So in fact, for the purposes of this theorem, exceptional could be replaced with just don't have F a polynomial and alpha the point at infinity, right? Because if you do that, then you just keep getting the point at infinity when you take inverse images. And that's the only actual exception here. So being an exceptional point is a tiny bit more subtle, but not much more subtle than that. So just think of the point at infinity for polynomials. So in other words, this very natural number theoretic question where if you build this sort of iterated pre-image tower, when do you get a finitely ramified extension or an extension ramified over infinitely many primes? And the answer is just whether or not this function is post-critically finite. So, and in fact, one of these directions, so the if direction, so if f is PCF, then you get this finite ramification property. That direction is sort of, that was the direction proven first by Aiken, Hajir, and Mayer, and Cullinan and Hajir. And there you can replace P1 by like any smooth projective variety. And maybe I'll mention later what the definition of post-critically finite would be there. But it's the other direction, which is maybe a little bit more subtle, that this finite ramification of this algebraic extension really does give you post-critical finiteness for F. But again, alpha here is not a critical point, right? So this is something about the orbits of the critical points telling you something about the backwards orbits of all the points. So again, the critical dynamics. So I guess in arithmetic geometry, we sometimes say that the geometry determines the arithmetic. And so maybe here, the critical dynamics determines the dynamics in general, in some sense. Are there any questions at this point before I continue?
It's looking great, Patrick.
Okay, thanks. So hopefully you have some reason why these may be interesting, and you can even sit down after the talk, of course, and try to write down examples of these sort of PCF polynomials or rational functions. And for rational functions, you can see that it's quite tricky. And I have not given you any examples of rational functions, but there are many. To give you a little bit of a sense, though, of how big the space of these things is, I want to mention a result of Thurston from complex dynamics, that there are no non-trivial algebraic families of these PCF rational functions. The exception are the flexible lattice examples, which I'll define on the next slide. But other than these sort of well-known exceptional families, these PCF examples don't come in algebraic families. They're not deformable. They're just a whole bunch of isolated examples. And actually, one thing I am just reminded of right now is that I should just open the chat window in case anyone asks me questions in the chat. So sorry, somehow the chat window closed on me. Okay, and so what's the intuition behind this statement? Well, basically, if you sit down and try to figure out how many degrees of freedom you have in specifying a rational function of degree d, it's 2d minus 2, once you take into account the degrees of freedom that are killed by working independent of choice of coordinates. And 2d minus 2 is also the number of critical points that a rational function of degree d has. So you have the same number of, if you're imposing conditions on those critical points, you have the same number of conditions as dimensions. And so you might expect that any particular diagram that you write down, like the ones on the previous slides, will cut you down to a zero-dimensional set of rational functions which satisfy that. And that's more or less true. But first of all, the actual theorem is not that easy to prove. And one of the hints that it might not be that easy to prove is the fact that there are these exceptions. And so I'll tell you what those exceptions are. What are these flexible lattice examples? If you haven't seen these before, there's a sort of general way of constructing a mysterious looking rational function of one variable about which you can say a lot. And that is the following. So if you take an affine map from an elliptic curve to itself, which commutes with -1, then here I have the x coordinate projection. And that commuting with -1 will give you induce a map here from P1 to itself, little f. There's no big F, so it's just F. And the dynamics of F here is, of course, closely related to the dynamics of whatever this affine linear map from E to E is. And it turns out, sorry, Adam had a question. Yes, the slides are available online, by the way, if you want to be able to flip back and forth. You can also ask me, but Adam asked on the PCF maps and number theory slide, what is K? So there I sort of kept it deliberately vague, but in the statement of the theorem, let's say K is a number field. And you can ask the pre-images question, I guess, for any field, but a number field is what I'm using to sort of get the motivation for the number theorists. Characteristic 0? I think we should say characteristic 0. Yeah, thanks, Adam. For now, we'll say characteristic 0, because otherwise I'm gonna get myself in trouble. And so here, if you take this particular affine map, let's say n times p goes to n times p plus a point of order 2, that's something that survives quotient y plus or minus 1. And that'll give you a family where you can vary the elliptic curve and you get a properly varying, like an honestly varying family of endomorphisms of P1. And these are the flexible lattice examples. And they're always post-critically finite. And they're sort of the exceptions to basically everything in this talk. Okay, so now, since this is sort of a primarily number theoretic audience, I think the heights background will be a lot more familiar, but I'm still going to just go through this quickly as a reminder to get everyone sort of on the same page. I want to talk quickly about heights because I'm going to talk about ample heights on at least one variety. So starting at the basement and going up to the top floor in one slide, if A over B is a rational number in lowest terms, then the height of A over B is the log max of absolute value of A and absolute value of B. So it is actually the size, whatever, by some linear factor. It's the diameter of that circle that LaTeX wants to put around that number in the diagrams I was drawing. And okay, on n-dimensional projective space over Q, you can make the same sort of definition. So if you have some point in projective space, you can scale the coordinates so that they're all integers and they have no common factor, and then the height is just given by this. And I then want to make two generalizations of this. So this is the height on Pn of Q. There are sort of two generalizations that I want to make. One is if you have a projective, or if you have any subvariety now of Pn of Q, of course you can restrict this height function to that subvariety. And if you have a projective variety, or just a variety with an ample class on it, that ample divisor, ample line bundle gives you many choices of embedding of that variety into projective space. And so that gives you a bunch of choices of height functions. And for the same ample divisor, if you normalize it, you sort of always get more or less the same height. So when I talk about a height on a projective variety relative to an ample divisor, if you're not sort of familiar with that language, you can just think of your projective variety as already being a subvariety of Pn. And then here's my nice height function on Pn. And of course, I can apply that to points in a subset. And then, of course, the height function also extends to Q bar. And that's not a hard extension, but if you haven't seen it before, I didn't want to put it on this slide. But you can also talk about heights of algebraic points. And why are we interested in heights? Well, the primary motivation, I think, for introducing heights is that sets of bounded height over a number field sets of bounded height are finite. So this is the Northcott theorem. I like to stick they in there. Or more generally, if you're looking at algebraic points, sets of bounded height and bounded algebraic degree are finite. And so this is sort of a nice way of proving finiteness. For example, the Mordell-Weil theorem for elliptic curves. The way you really prove it is you prove that the Mordell-Weil group is generated by a set of bounded height, right? And then the fact that that set of bounded height is finite gives you the finite generated set, sorry, finitely generated group. And again, this is actually not that hard to prove, right? This is done fairly easily by reducing this to showing that there are only finitely polynomials up to a given degree with coefficients bounded by something. So heights are going to come in here basically as a measure of arithmetic complexity, but also just because they allow us to prove finiteness results. And now I want to introduce a slight tweak of this basic height function, which is going to be useful in arithmetic dynamics. And it depends how many names you want to stick on here. But I say this is due to work of Néron, Tate, Denis, Call, and Silverman. You can associate to any rational function of degree at least 2 a quote unquote canonical height function. So that's this thing here. And the observation one makes is that if you look at the height in an orbit, it grows like d to the n times something plus a bounded amount. And the bounded amount depends on f. But this coefficient here of exponential growth is going to be, I mean, you can sort of look at this and post hoc define it to be this divided by d to the n after n goes to infinity. But this is, we're going to call the canonical height. And it tells you how quickly the orbit is growing in some sort of asymptotic way. And it's pretty easy to check from the definition here that this canonical height is non-negative. It doesn't differ from the usual height too much. So the difference between the canonical height of P with respect to F and the usual height of P is bounded in terms of F. And finally, this is going to vanish. Well, if you have a point which is pre-periodic, you only get finitely many things on this side. And so for this asymptotic to hold, this thing has to be 0, right? Otherwise, this is definitely going to infinity. And so in fact, that's an if and only if. So the canonical height vanishes if and only if the point is pre-periodic or has a finite forward orbit. And that's the other direction is a simple consequence of this theorem of Northcott. So at a conference, and this is in 2010, I think maybe March of 2010 or something, so it's very close to exactly 10 years ago. Joe Silverman proposed this critical height of F, measuring the sort of dynamical complexity of F in general, not with respect to a particular point, by summing the canonical height evaluated at all the critical points. And there's a couple different reasons why this might be natural definition. The main one, I would say, at least now, is that we have this impression that the dynamics of the critical points tells you a lot about the dynamics in general. So maybe the canonical heights of the critical points tells you a lot about the canonical height in general, or about the arithmetic dynamics in general. The other reason is that if you want to think of some kind of obviously marked points that have something to do with F, there are not that many choices. So you could look at, say, the fixed points of F. That's a sort of natural set of marked points, but they all have canonical height 0. So you're not going to build anything interesting by evaluating the canonical height there. So the other reason to sum the canonical heights of the critical points is it's sort of the most obvious natural set of marked points that doesn't make this trivial. And one quick observation is that this is independent of the choice of coordinates. So if you do a change of coordinates on F, and I guess I haven't written this down explicitly, but that means the same change of coordinates on the domain and range, right? A Möbius transformation on both sides, the same one, so that I can iterate. And it's easy to check that this side, like the canonical height, is sort of equivariant, and so are the critical points. And so the critical height is invariant. And so it gives us a nice, well-defined function on the moduli space. So now I'm introducing this in a sort of backhanded way. It gives us a nice, well-defined function on the moduli space of rational functions of degree D modulo change of variables. And I know that Joe Silverman will be giving a talk about moduli spaces in this seminar series. It's the next talk. And so I won't go into the construction of this moduli space, but it's you can think of it as just some set of equivalence classes of rational functions modulo change of variables, but it turns out that you can give it the structure of an affine variety. Okay, so in some sense, the main motivation for this talk is a conjecture that Silverman made at this conference in 2010 in Barbados. I'm always obliged to mention. So it's surprising that we can remember the conjecture or anything that happened. But anyway, on the sunny beaches of Barbados, this conjecture was made. So the critical height is sort of a natural candidate for a nice quote unquote height function on MD, right? So it has some nice properties. It interacts nicely with iteration, which, for example, if you do something naive, like look at the height of just the coefficients that define a rational function, this first statement, I don't know, it's some sort of, there is probably some way of relating the height of an iterate to the height of the original thing, but it's going to be some nightmare. Whereas here, this is an easy application of the chain rule. And similarly, the critical height vanishes exactly at these post-critically finite rational functions. This is now in the context of Q bar, precisely because the canonical height vanishes exactly at pre-periodic points. But this is so far a height in name only, right? There's no reason to believe that this is an actual height function that comes from some actual embedding of MD into projective space. And so this conjecture was made at a conference in 2010 by Silverman that basically this critical height should be asymptotically commensurate to any ample VaNTAGe height. And here what I mean is like the height is, you know, these are real valued functions, and I mean that each one is bounded by a linear function of the other. And of course, you need to know in advance that any two ample heights on MD will be held in this relation, because otherwise this is not going to be true. And this is spectacularly false for the lattice examples, but that's, so we make an exception for the lattice examples. So this is a conjecture that was made in 2010. And again, there are a lot of different reasons why you might make this conjecture. In some ways, this theorem of Thurston gives you some motivation for this conjecture. In some ways, it's the idea that the critical dynamics sort of determine the dynamics in general, so that the sort of ample V height on MD will come up in a lot of height estimates involving the arithmetic dynamics and orbits at any point. And so it's nice to be able to sort of swap that out with the critical height. So this was the conjecture. Are there any questions before I move on to the next slide? So again, if you have conjectures, feel free to type them in the chat as well. I'll try to keep my eye on that as we go.
Yeah, it's going really well, Patrick.
Okay, so I'm going to sort of cut a long story short in some ways. So theorem, the conjecture on the last slide is true. And so I've given whole talks that live between these two slides, but I didn't want to do that today. So the statement here, sorry, the abbreviation is basically that this conjecture is true as stated. So any ample height on MD is comparable to the critical height, except on the locus of Lorentz maps. And maybe I'll just go through briefly the sort of history or the sequence up here, because I've listed 4 different papers. So this was established first for polynomials, and the proof for polynomials, as I mentioned here, is at first, at once a little bit simpler, or maybe much simpler. There's not a lot of dynamics that actually goes into the proof. In fact, other than maybe the construction of the canonical height itself, there's no dynamics that goes into the proof in the case of polynomials. But on the other hand, there are also extra corollaries, which I'll mention maybe on the next slide. Yes, on the next slide. So that was this first example. Rafe Jones, Alan Levy, Rob Benedetto, and I, a little while later, proved this consequence. So the non-Lorentz PCF maps are a set of bounded height, which is basically saying, I mean, this is sort of the motivation, or one of the motivating consequences of this conjecture was this fact here, that the non-Lorentz PCF maps would then be a set of bounded height, and so you get a finiteness result for post-critically finite rational functions. And that's just saying that this asymptotic is true when the right-hand side happens to be 0, which is still non-trivial, right? I mean, it's giving you some boundedness over here. And then the full conjecture was done a couple of years later using essentially the same tools. And those 2 papers, the proofs were much more fundamentally dynamical. So they're somehow deeper than the case of polynomials, but at the same time, they lack some of the additional corollaries, which I'll mention on the next slide. And finally, there's a much more recent paper. This is a preprint. So my plus here means that this is like a preprint date. And this is, as far as I know, not appeared yet. By Thomas Gotye, Yusuke Okiyama, and Gabriel Vigny, gave a new proof of this theorem with some additional results, basically getting around some of the dynamical machinery which we use, and giving sort of effective bounds where we gave ineffective bounds. Okay, so that conjecture of Silverman's is true. I want to say a little something about the additional, just to give you some sense of the flavor, the quote unquote bonus corollaries that you get in the polynomial case. So they basically have to do with good reduction and maybe some applications in the context of complex dynamics. So a rational function P has good reduction, rational function F, I guess, has good reduction at P, basically if you can reduce it mod P and things don't go sideways, right? So you can reduce it mod P and you get a rational function of the same degree. And potential good reduction means, okay, maybe you don't have good reduction, but you can do a change of variables, maybe over some finite extension, which gives you good reduction. So potential good reduction is, you can think of it as well as this extending to an endomorphism of schemes from P1 on the generic fiber to P1 over the local ring you're talking about. And so one of the corollaries, the extra corollaries that I mentioned for the case of polynomials, is that you get this nice statement that a post-critically finite polynomial actually has potential good reduction at any prime bigger than D. And this is connected to the local contributions to heights. It's basically, another way of saying this is that the critical height has the naive height in a certain normal form has no non-trivial contributions outside of a certain finite set of places. But you can rephrase that in terms of this potential good reduction. And I just wanted to contrast that. So it's not just that we didn't get that same corollary for rational functions. You can in fact show, so I write example here, but this is clearly a statement, not an example, but it's proven by a family of examples, you can show that not only is this statement false for rational functions, but in fact, no statement like it is true for rational functions. So in fact, for any D and any finite set S of primes, there exists a post-critically finite rational function of degree D, not a polynomial, and some prime outside of S at which F does not have potential grid reduction. So that's kind of an interesting contrast, and maybe I'll come back to this near the end. I want to sort of emphasize the fact that there are other questions sort of related to this that are still not quite understood. So the good or bad reduction of post-critically finite rational functions is not really well understood at all. We just know that it's not as simple as the polynomial case. Are the counterexamples non-lattice? Yes, they are. Yes. So a question from Clay Pecci was, here are the counterexamples non-lattice? Yeah, actually, now that I think about it, I guess you could pretty easily construct counterexamples here using lattice maps, but the counterexamples are non-lattice. Yeah. In fact, the counterexamples, I'm trying to recall the exact construction, but they are very close to being polynomials, in the sense that polynomials, if you want to think about them in a coordinate-free way, polynomials are just rational functions with a totally ramified fixed point. And the examples here are rational functions with a totally ramified point of period 2. So in some sense, they're very close to being polynomials, but they're not lattice examples. Yeah, so thank you for that. Okay, so I want to talk. So I'm gonna move on to these questions in higher dimension. But before I do that, I want to mention some more work in P1 that's still sort of ongoing. So we have an answer now to this conjecture of Silverman, but there's still a lot of interesting questions over P1 about the dynamics of critical points and critical heights and so on. And in particular, I want to mention basically the dynamical Andre-Oort conjecture, in part because I think during Holly's talk 2 weeks ago in the chat, it was advertised that I might talk about this. So now I am. I'm sorry, I just noticed there are two questions. So David is intuitively, what is the reason for that contrast between polynomial and rational functions? That's a good question. And I don't know if I have a good intuition for what the reason is. Maybe I'll say something more about that at the end, but I don't have a good intuition for what that contrast is. And is there a similar coordinate invariant definition of lattice maps? So there is, I mean, yeah, there are ways of characterizing lattice maps. I don't know the exact statements, but there are ways of characterizing lattice maps by a sort of combinatorial description of the critical orbits. And so maybe that's a coordinate invariant definition of lattice maps, although maybe it's more of a fact that things with a certain post-critical combinatorics have to be lattice examples. But I don't have the description or the characterization on the top of my mind. Are there any other questions before I go forward? I just want to briefly mention this sort of unlikely intersections type questions. The usual definition as the quotient of a toral endomorphism is coordinate invariant. Yeah, so yeah, I think the way I describe lattice maps, I was particularly taking the x coordinate projection, but there's sort of a but there's already sort of coordinate independence in the initial definition of the usual definition of a lattice example. Okay, so let me just very briefly mention this dynamical Andre-Oort conjecture. So let's imagine now that we have a one parameter family of rational functions. And from this result of Thurston, we know that except for these lattice examples, which I'm going to ignore, your one parameter family of rational functions can't all be post-critically finite unless it's like a constant family or something like that. So in general, the set of specializations which are post-critically finite is going to be a set of bounded height as a consequence of this conjecture of Silverman's, which is now a theorem. But if you actually try to write down in a one parameter family what it would take for a given instance to be post-critically finite, so if you impose some finiteness condition on one of the critical orbits, that's like the vanishing of some function on this curve. And then if you impose a condition on another critical orbit, that's the vanishing of another function on this curve, and you want those two things to coincide. And of course, there are many different conditions you could put on each critical point, but nonetheless, you're sort of choosing from a countable menu, you're choosing all these conditions, most of which are going to be incompatible. And so this sort of fits naturally into the intuition of unlikely intersections, that somehow, even though you have countably many times to have this improbable thing happen, unless there's a particularly good reason, it should still happen only finitely often in general. So the PCF points in a one parameter family like this are vastly over constrained. And so again, the sort of unlikely intersections philosophy, the philosophy I think of as, there shouldn't be infinitely many of these things unless there has to be, tells you that maybe you should expect for typical one parameter families, and I'm being intentionally vague here, for this set to be finite. And so I do want to sort of mention a few results in this direction. So here's the conjecture, the dynamical Andre-Oort conjecture, which says what I just said. And again, I'm keeping it a little bit vague because I don't want to attribute a specific falsifiable statement to somebody else right now. But I want to give you some indication of results in this direction, which sort of lend support to this idea. And so here's one example. So this curve, let me tell you what this is, pair one of lambda. If you have a rational function and you're thinking about it in a sort of coordinate-free way, and you have a fixed point, then you might as well take that fixed point to be at 0, and then your rational function is going to have some local expansion like this. And lambda here sort of determines the local behavior or the local flavor of the map around that fixed point. And pair one lambda in the space of cubic polynomials, so the space of cubic polynomials is two-dimensional, pair one lambda is the curve of examples with a fixed point of this particular multiplier. So you're fixing some number lambda, and you're looking at the curve this defines. And in general, if you fix this thing here, that's not telling you anything about critical points. And so you expect that to not be one of these critical orbit relations. And so you'd expect a typical curve like this to have only finitely many post-critically finite points on it. And it turns out, this result of Baker and DeMarco from 2013, that's exactly, your intuition is exactly right, that pair one lambda contains only finitely many post-critically finite points, unless lambda equals 0. And why lambda equals 0? Well, because if I specify that lambda is 0, then I'm specifying that f is a critical point. And so if I'm specifying that a fixed point is a critical point, then I'm also specifying that a critical point is a fixed point. And so that is a critical orbit relation, right? So this theorem here sort of confirms this Andre-Oort philosophy, or that it says exactly what you'd expect it to say for these pair one lambda curves. And shortly afterwards, so the space of quadratic rational functions is another two-dimensional moduli space. And so again, pair one lambda is a curve. And I guess shortly afterwards, DeMarco, Wang, and Ye proved the same thing there. And I'll mention a few other results in this direction. So pair n lambda is the same curve, but now instead of a fixed point, we're talking about a point of period n. So in fact, you can extend this result to the curve where you have a periodic point of a given multiplier in the space of cubic polynomials. So again, this is confirming that exactly the one of these curves that you think might have infinitely many PCF points, that's the only one that does. And this was proven sort of independently and simultaneously by Favre and Gotye and Hyoka and Yi. And then here's a different result that's, I asked this question at an AIM conference. And this, if you know the original theorem of Andre, this looks quite a lot more like that specific theorem. So if you have a curve in the plane and you ask, this is over the complex numbers now, and you ask how many pairs AB have the property that Z to the D plus A and Z to the D plus B are, sorry, how many curves have infinitely many points AB such that Z to the D plus A and Z to the D plus B are simultaneously post-critically finite? Well, there are a few curves that have to, like horizontal and vertical lines, and a few diagonal lines. But Dragos-Gyoka, Hawley-Krieger, Kwang Wen, and Heshi Yi prove that, in fact, those are the only ones, right? So this is another one of these unlikely intersection results. And as you can see, there are sort of a lot of really nice, interesting partial results in this direction, but there's a lot more room here. One last thing I wanted to mention in this area before I move on to higher dimensional examples is a very recent paper, well, it's a book, I guess, of Favre and Gotye. So Favre and Gotye sort of give a fairly general statement about this problem for polynomials, in fact, a more general problem for polynomials. But I'll just mention briefly, without maybe going into all the technical details, that they give a sort of complete characterization of one-parameter families of polynomials, which can have infinitely many post-critically finite specializations. And so this first condition basically says your family is more or less an iterate of a family that also has that property. So the first condition sort of, in some sense, reduces you to the second condition. And the second condition says, okay, if your family on the generic fiber basically only has one free critical point, then every description of it being post-critically finite is really only imposing one condition. And so that's the vanishing of one function on your curve. And then you really can have that happening for every single choice of critical orbit. And so these statements are up to symmetries because there are things you can do. You can have polynomials that have two free critical orbits, but they're related by some sort of involution, and then they'll either both be finite or both be infinite, and you should really count that as one infinite critical orbit. And I'll just mention that as an example of a situation in which you can say that this second condition holds. If you look at this hypersurface pair n lambda in the space of polynomials of any degree, so it's the same definition as for cubic polynomials, but it's in general a hypersurface. If you pick a curve in there, then this condition will be met as long as lambda is not 0. So you can sort of generalize the previous statement about the curve pair n lambda for cubic polynomials to curves on the hypersurface pair n lambda for polynomials of an arbitrary degree. But there's still a lot of sort of interesting questions here. Again, I've been sort of intentionally vague about what I mean by asymmetry. But there are a lot of interesting questions related to complex dynamics, critical dynamics in the arithmetic dynamics world on P1. Are there any questions about this before I move on to higher dimensional questions?
Can you find some with three? Sorry, if you go back one slide.
Yeah.
I know one slide.
I went back 2 slides.
Yeah.
This one? Yeah.
Do you think you can, what happens if you ask for like 3 generically free critical orbits?
Yeah, so I actually have a sort of a conjecture that if you intersect 2 of these types of hypersurfaces, you should get, well, if you intersect k of these types of hypersurfaces, you should get k+1 generically free critical orbits. But first of all, I can't prove that. And second of all, there are a few special cases in which that's not going to be true. And I don't fully understand these are these sort of conspiracies, I think they're called in complex dynamics. There are times when you'll have 2 different pair n lambda hypersurfaces coinciding for unknown reasons, or at least unexpected reasons. But yeah, in general, I expect that if you keep intersecting hypersurfaces of this form, you should sort of keep getting more and more, forcing more and more independence. So in the last little chunk here, I want to talk about this question in the higher dimensional setting. Oh, Adam only knows of one conspiracy like this. I also only know of one, but I've been told that there are more.
This is Milner's peer 2 minus 3, peer 3, the one, yeah.
Yeah, so there's one particular one that's in a paper of Milner, but I was told by Thomas Gotye that there are more of these that he knows of. So, but that's the
really? Or did he find? I mean, because I've discussed it. Maybe I wonder what he means.
Yeah, I'm not sure. But if you ask Thomas, he will. Well, he'll either tell you.
This is recently you spoke with him. I mean, this work I certainly haven't heard him. So.
I think this conversation was 2 years ago.
I shouldn't be interrupted. Go on with your talk.
Okay. Okay. So I'll give some.
Got excited.
So sorry, there's another question. In the moduli space of functions, what does the locus of those with infinitely many PCF points look like? Is it algebraic? And if so, of what dimension? So in the moduli space of rational functions, the PCF maps are points, right? And so the locus of PCF maps is sort of this countable collection of points plus 0, 1, or 2 curves that come from these lattice examples. So the PCF maps are themselves points. And then the question, in some sense, this sort of dynamical André question is, which curves, if you want to state it for curves, which curves have infinitely many of these PCF points on them? Or more generally, I guess, if you take a collection of infinitely many PCF points and look at the components of its Zariski closure, what kinds of subvarieties of moduli space do you get? So I want to get onto the higher dimensional questions because I have a few results and a few sort of interesting directions to go. If you talk instead of an endomorphism of P1, if you talk about an endomorphism of Pn, you can sort of make the same definition in a kind of obvious way. So the critical locus here is just going to be the ramification locus. If you like, you can take the usual second-year calculus definition now instead of first-year calculus. You can take the Jacobian partial derivatives and look at where that matrix is singular, and that defines some hypersurface. And you can look at the forward image of that. And the sort of glib way of defining PCF-ness here is that if you just take the union of the iterated forward image of this hypersurface, it's a priori a union of countably many things, so it's not algebraic. But if it is algebraic, I'll call that thing post-critically finite. And so in higher dimensions, you can ask the same sorts of questions. What do the critical orbits tell you? Now I'm talking about the orbits of the critical hypersurfaces. And what sort of role does post-critical finiteness play? And again, I wanted to convince you that there are some of these things. And again, I choose a silly example to start. So the squaring map on P2 is, any powering map on Pn is post-critically finite. I wanted to give you a few other examples. So here's an example, and I will draw in the arrows here for you. So I have the morphism at the top there. And this morphism is ramified on the coordinate hyperplanes. And then you can just quickly compute where each coordinate hyperplane goes. And you can see that this example is post-critically finite. So all the ramified hyperplanes, or the whole ramification locus, eventually maps down to some fixed divisors. And I have another example. I thought it would be fun if I drew in the arrows, be more interactive. So here's another example. And again, I want to make sure that the iPad doesn't hide the actual morphism itself, but it's up here in the title bar. And you can just sort of compute where everything goes. And again, everything here falls into a 3-cycle of hyperplanes. And so again, this is another post-critically finite example. So there are at least some of these things in higher dimension, more than just the power map. I have one more because people might be getting suspicious that it's always a hyperplane or a collection of hyperplanes. Here's an example of, again, this looks very similar to the other two examples, in part because I'm doing all quadratic maps here. But here's an example of an endomorphism of P2 that's ramified along this hyperbola and the line at infinity, and the hyperbola maps onto some curve, which is sort of miraculously fixed. Okay, so you can ask about these PCF maps in higher dimension and ask what you can say. And one thing I want to point out sort of quickly is that there's some reason to believe that these things are a lot less common in higher dimension. So there's a sort of folklore theorem. It's true, but it's always a question of who we attribute it to exactly. I think Adam Epstein is actually the one I heard it from, that endomorphisms of P1 that are post-critically finite. In fact, even if you just look at periodic critical locus, those are Zariski dense in the moduli space. So they're in some sense.
I think what happened, as far as I remember, Joe, there may well be some history of this, but I was on the beach probably with you and Laura, but definitely with Joe in Barbados. And Joe asked this question, and Laura and I just made up things on the spot. It happened to be 2 different arguments, right?
Yeah.
And we sort of agreed it was a fact, right?
Yeah, so folklore maybe plus beach.
It became folklore at that point, but I'm not sure I ever heard anyone pose the question before, I guess is what I'm saying.
Well, so the interesting thing is that it turns out that this might not be true for post-critically finite endomorphisms of Pn when n is at least 2. And so here, for technical reasons, we need the degree to be at least 3. And here we're talking really about periodic critical locus or periodic after 1 or 2 jumps. So this is slightly more restrictive. but not more restrictive than this, even this statement up here. So the point is just in higher dimension, these things might be much more rare. And so there's some question about whether we should be thinking about characterizing the post-critically finite maps in particular, but this critical height is still an interesting quantity to look at on Pn. So the canonical height that I mentioned for points on P1, you can extend this not so easily, but this was done by Shouwu Zhang for subvarieties. And so once you have a canonical height for subvarieties, there's a sort of a natural definition of the critical height of an endomorphism of Pn, right? So you can take just the canonical height of the critical divisor, and you can decide what you're going to do about multiplicities. And you can even make this more concrete. So the height of a divisor, you can define to be the height of the tuple of coefficients of any defining homogeneous form. And then you can sort of give almost a post hoc definition of Zhang's height, at least for divisors, that looks very much like the definition you might give for points. Okay, so it certainly makes sense to talk about the critical height of an endomorphism of Pn, and it has some of the same properties as in the P1 case, so it's easy to check that it behaves nicely under iteration. It vanishes on these PCF examples. I don't want to say exactly. And it's bounded above by any ample height on the moduli space. And so the natural question is it actually asymptotically comparable to any ample height on the moduli space? So here's a sort of very natural generalization of this conjecture of Silverman's. Is it true that there's a proper Zariski closed subset of moduli space such that any ample height is sort of commensurate to this critical height off of that proper Zariski closed subset? And I think this is, I mean, you can ask how that relates to the Zariski density or non-density of the set where this vanishes. But this is sort of a separate question. And maybe I'll say, I'm willing to just request that Z be the natural generalization of Lattice examples. But if you want to be more cagey about your conjecture, you can always say an unknown Zariski closed subset. So what I want to do is mention just one or two cases where we can say something about this. The first case is a little bit artificial, but if you take a one parameter family of endomorphisms of Pn, you can show that the critical height varies very naturally with respect to the height of the parameter. And so this is a sort of a variation on a result on variation of canonical heights from Joe Silverman's thesis for heights of points on elliptic surfaces, heights of sections, right? So the points on the elliptic curves. And so if you have a one parameter family where the critical height does not vanish on the generic fiber, and so here I just mean this height is going to be computed with respect to the height function on the function field, then this conjecture is sort of true in any one parameter family, but your constants depend on that particular one parameter family. So there's maybe some, vague intuitive heuristic reason why this conjecture might be true, or at least it doesn't fail in some obvious way for one parameter families. But it turns out there's another setting where we can say a little bit more, and maybe I'll wrap up the talk with this. So Milner has, again, in the complex setting and the one variable setting, Milner has this nice paper where he looks at so-called bycritical rational maps. Right? So if you have a rational function of one complex variable, it's going to have at least two critical points. But there are some that have exactly two critical points. And if you're interested in studying the dynamics of the critical points, that makes things simpler. If you have exactly two critical points, you move them to 0 and infinity, and then you can sort of more explicitly describe the complex dynamics. And so he called these bycritical maps. And so I started thinking about the natural generalization of this to Pn. So let's say, and I call these minimally critical maps, and I was almost going to do a little like Zoom poll here to see if I should change the name, but I won't do that in the interest of time. So I'll call these minimally critical maps until somebody comes up with a better extension of bycritical, like n+1 critical or something. But the natural generalization is an endomorphism of Pn, which is ramified along exactly n+1 hyperplanes. And if you do a little shuffling of coordinates, you can sort of, without loss of generality, take those hyperplanes to be the coordinate hyperplanes. And then your function has the form a times x to the d, where A is an n+1 by n+1 matrix, an element of PGLn+1 here. And x to the d is just the coordinate-wise power map. And just to convince you that, again, I wanted to make sure that statements I make are not sort of completely vacuous. It turns out that there are PCF examples of this form. So here are 6 examples from the literature of PCF maps of this form. So here, these are all, so the function I'm thinking of is this matrix times x squared. So in other words, the squaring map on P2 followed by the linear transformation implied by these things. And it turns out all of these examples are PCF. So this example and this example I've already shown you on previous slides. These come from a paper of Fornes and Sibony. Here are 3 examples that appear in a paper of Dupont, but they're coming from an earlier paper of Ueda, and Belk and Cook give us this example. One thing I'll mention is that there should be a 4th example here. In fact, all of these examples have the sort of peculiar property that if you follow them up with any row permutation, you still have a PCF example. And they're different, they're dynamically different, but there is a 4th one here. I mean, there should be 6 because there are 6 ways of ordering the rows, but some of them are related by change of coordinates. I will also mention that this example and this example can be sort of generalized to any dimension and any degree. So you have, certainly these minimally critical examples contain sort of non-trivial post-critically finite examples in any dimension and any degree. And it turns out that here, in this context, you can prove exactly this conjecture. So the critical height is a moduli height for these quote unquote minimally critical examples, with one little condition here, which is that, whoops, I normally have a condition d at least 2, and for this particular result, for reasons that show up in the proof, I need d to be somewhat larger than 2. And I don't think, this is not a fundamental thing, like I don't think it's false for d smaller, but my proof does not work for d smaller. But here's at least one sort of, not one parameter, but one larger higher dimensional family of semi-natural endomorphisms of Pn for which you can establish this conjecture of Silverman's. And so I guess I wanted to end the talk by thinking about some further directions. And rather than show the following 5 slides, I'll just mention that one sort of natural, another natural family, well, maybe I'll go to the last slide and mention another sort of natural family. So I got to this family of examples by first thinking about examples of this form where one of the hyperplanes is fixed. So instead of the power map followed by a projective linear transformation, I was thinking about the power map followed by an affine linear transformation as an endomorphism of AN. So that's a subset of these things. And you can actually prove stronger theorems in that setting. But there's sort of a natural question there of, if you have an endomorphism of Pn with an invariant hyperplane, then restricting to that invariant hyperplane gives you an endomorphism of Pn in dimension 1 lower. And then there's sort of this natural question of, how does the critical dynamics or the critical height relate to the critical height or the critical dynamics in dimension 1 lower. So maybe I'll end with those conjectures. Actually, I'll just skip ahead to the last slide. In the case where one of your hyperplanes is invariant, in that theorem I just stated, you can actually prove it all the way down to d equals 2. And so there's a natural question there of how much you can leverage the existence of an invariant hyperplane. And so I wanted to leave off with 2 conjectures that I thought might be a little more tractable than this general conjecture of Silverman's. And one is, if you have an endomorphism of Pn with an invariant hyperplane. Well, of course, this conjecture of Silverman says that you should expect this critical height to be comparable to the moduli height in general. But I'm going to propose something that I think is more tractable, that this critical height is comparable to the moduli height, plus some information about what's happening on this lower dimensional hyperplane. And similarly, you might sort of want to extend this Thurston rigidity type result to Pn. There's sort of a natural analog there for a conjecture. Maybe on Pn, the only 1 parameter families of PCF maps are lattice examples. And again, here, I want to propose this idea that, well, if you look specifically at maps with an invariant hyperplane, maybe you can have at least, maybe it would be easier to prove sort of relative rigidity. So the only non-isotrivial families of PCF maps in this case are those that are already non-isotrivial at infinity. And so having knowledge of the non-isotrivial families in one dimension down maybe allows you to sort of conclude something in this dimension. And so with that, I will leave it there. Thank you.
Oh, thank you, Patrick. And I think there's one unanswered question in the chat. Can you read the question?
Yeah, so there's a question in the moduli space of functions. What does the locus of those with infinitely many PCF points look like? Is it algebraic? So the, I mean, the PCF points in the moduli space are themselves functions, right? So they are rational functions with this post-critical finiteness property. So the PCF functions are points in the moduli space itself. And so, I mean, all of these moduli spaces have infinitely many PCF points. And then when you sort of look at subvarieties, that's when you get these interesting Andre Oort type questions. But I think that's the best answer I can give there.
I mean, the post-critical points are in the dynamical space, but there's only finitely many of them. But there's infinitely many parameters where that's happening. Is what Patrick is saying.
Yeah, yeah. So the post-critical points are the points in the dynamical space. The post-critically finite maps are the maps themselves in the moduli space.
Oh, there's another question in the chat. Holly, do you want to read this, or do you want Patrick just to read it?
I can read it. So Holly asks, might the critical height on moduli satisfy a lamer type lower bound? So that's a good question. Let me just mention what that might be for people who are not so familiar. So I'm going to just say lamer, but this is I think what Holly means, I think, by a lamer type lower bound. So one might conjecture that if the critical height is not 0 for a given endomorphism, then the critical height is at least some constant divided by, oh, let's start over Q, the degree of the field over which this thing's defined. Yes, and Holly says that's yes, what she means. So might this be true? I think yes. In fact, it's maybe not obvious. So you can show that the critical height, you can make it this small. This is maybe not the right notation of what I'm trying to say. You can show this infinitely often. I mean, it's not always true, of course, but you can show this, which, yes, epsilon here should depend on D and also depend on N. So in the P1 case, it's not even trivial to sort of construct examples that show that lower bound is the right asymptotic, but you can do that. And then in the other direction, I think there's very little known. I suspect it's true. And I do have some old results that I haven't published for unicritical polynomials, which don't give you this, but they give you something kind of in that direction. So that I think is the right asymptotic. So I think that's a nice question also for future research. What can you say in this direction? So Faye who asks, in the theorem about minimally critical maps, there is no exceptional set like the Lattez. That's actually a really nice question. Thank you. Whoops, I went past it. So here in this statement, you will notice that there is no exceptional set like the Lattez examples. And that is true. And so I guess the conclusion you can draw from that is that there just are no one parameter families of Lattez maps that have this special form. And so in fact, if you go back to this previous slide, this paper of Dupont, what Dupont is showing in this paper is he hauls out these 3 examples of Weta and shows that they are all Lattez examples. and also shows that one of these examples of Fournier's and Sibony, I can't remember which one, let's just say it's this one, is not a Lattez example. So there are both Lattez and non-Lattez examples of this form, but there, I guess, are not enough Lattez examples that it would violate this theorem. So there are a handful of Lattez examples.
What is the definition of Lattez in higher dimensions? I don't think I've actually heard an official definition.
Yeah, so the definition of Lattez here is you have, so I guess we're working in complex land, you have a complex torus of which Pn is a finite quotient, and you have some torus map. Yeah. So
Oh, okay, but it wouldn't, I mean, so it could be finite, it's not necessarily a quotient by an involution. I mean, I just can't do the algebraic geometry in my head. Maybe you would never get Pn that way. I don't know. But.
Yeah, it's a finite. It's a quotient by some. It's like some Galois quotient by some finite group of.
So there's going to be different varieties, different sorts of them, I suppose, depending on the group action.
So these three examples all come from the square of one of my favorite elliptic curves.
Yeah, sure. There's going to be product examples. I don't really need a definition for that. You can fake that, and then but there's going to be other ones,
right?
That are somehow new, right?
I haven't checked this exactly, but these examples I think do not come from, say, the symmetric square of an endomorphism of one copy of this elliptic curve. It's really some endomorphism of this product of elliptic curves and some quotient which is not just a quotient in each coordinate separately.
Oh, I see. You can start it still, doesn't have to be a general abelian variety. You can just start it still with the product of elliptic curves, but then a morphism which is not a product of endomorphisms.
Yeah, exactly. Yeah, and I believe
gives you a natural family to play with. You're saying that you're saying all of those quotients can be expected to behave in a lot. I don't know what that means to be. I mean, I see. There's sort of manifest non-trivial families when you vary the moduli. You can just do this construction uniformly.
Yeah, exactly. Yeah.
Right.
Yeah.
So that doesn't even require a definition. That's kind of just an observation. Yeah. Okay. Good.
Yeah. Yeah. But again, somehow that does not. Those one parameter families just don't come up in this subfamily.
Well, thank you again, Patrick. This was a really nice discussion afterwards, and we will meet again in 2 weeks, I believe, to hear Joe Silverman.
Thank you.
Have a great day.